This is the meaning of what is this? A positive definite matrix. Okay. One of the very important lemma, which is called Schur complement lemma, that is highly required in case of robust control or control theory where we need to simplify many matrix things. Okay, and now you see, this is Schur complement lemma, and this particular relation. So this is called, the first one is the Schur complement of the matrix with respect to Q. Once again, Schur complement of the matrix with respect to Q. Because here we are considering Q inverse. So it has a nice pattern of going clockwise. You just mark which one is invertible. That is, here we have considered both of them invertible, but a weaker version is also there, where if one of them can be semi-definite as well. Okay, I will write that later. Suppose at this moment, if this is positive definite, then you start from the element which is diagonally opposite. Okay, so you see I am starting with R. Then you have to always move into clockwise direction. So after R, which is the element coming? S transpose, then its inverse exists, so we have to take this inverse. So S transpose into Q inverse into S. Okay, so that relation is called the Schur complement of the matrix with respect to Q. The same thing, if you wish to do with respect to R, then from which element you should start? From Q. So then after Q, which element is coming? S. So Q minus S into inverse of this element, R inverse into S transpose. Okay, so this is Schur complement of the matrix with respect to R. Now exactly in that way it comes. So that's why I said that is, if you know that one, then you don't have to remember this one, because at this moment when we are considering here that x in A11 is invertible, and then immediately the relationship will start from A to 2, and then suppose this element is there, then the x is the Schur complement. Okay. You see, that is, if you see the first supposition of lemma to A.2, if A11 inverse and X inverse exists, then the formula exists. See, that is once again the lemma A.2, I mean relation A.7. If you have any doubt in understanding, please ask me. Once again, that is page 511, okay, lemma A.2 and the relation A.7. If A11 inverse and X inverse exists, then the inverse of that partition matrix is that whole big chunk. Now here what did I write? If you consider that is one of the elements being 0. So the first one is the upper triangular partition matrix, the second one is a lower triangular partition matrix. In such cases, the formula, it really simplifies, and they are like this. Okay.
So what does this triangle about equals to
Sorry, once again.
X equals to triangle. What does this?
Oh, that is like X is a symbol which is defined this whole thing. This is means by definition. When we use something that is simply equals to mean assignment, okay, and then if it is by definition, then we write either this one or colon equal to, okay. Now, since here I have used the positive definite matrix, we should know the meaning of a positive definite matrix. Can anybody tell me that what is a positive definite matrix?
All active values are positive.
That is one of the distinguishing properties, not the definition.
If X transpose A
You have to start in that way. So, definite definition of a positive PD matrix. Let M equals to M transpose belongs to R n cross L. At this moment, I have taken the field to be real, but it can be complex as well. Okay. Then M is said to be a positive definite matrix if A transpose Mx is greater than 0 for all x now to x not being identical to 0. Okay, that is the definition of a positive definite matrix. If it is with respect to C, then it would be Cn comma m cross n, and here also it will be Cm. Okay. Here you see the symmetry is very important. We are defining positive definiteness for symmetric matrices only. And if it is for the complex matrices, here you will have to write let M equals to either NH, that means Hermitian, or sometimes we write M star. M star means complex conjugate transpose, okay? Belonging to C n cross n. This H means Hermitian or this star means complex conjugate transpose. Both of them carry the same meaning. Okay. Now, can anybody tell me that is why this assumption is required?
Order will not match. Dimension will not match.
No. Here, what is the problem with the dimension? Because it is for the square matrices only. I asked, that is, if this symmetry or this Hermitian property is not assumed, then what problems we may face?
If we take the transpose of the equation, then it won't be like x transpose and x all transpose will not be zero.
But it may happen that is for like some square matrices. Just let's say if you consider this one, that is 1, 2, 0, 2. This is not a symmetric matrix, but still its eigenvalues are positive, and for all vectors you will find that this is like x transpose into x will be always positive. I am asking why this symmetry condition has been imposed. The reason is it's a sufficient condition which guarantees that all the eigenvalues would be real. That is the, once again, that is this symmetry or Hermitian property, that is a sufficient property or the sufficient condition for guaranteeing all the eigenvalues to be real. Please underline the word sufficient. Why? Because even if it is not there, still we can get real eigenvalues. This is an example. Okay. So that's why this symmetry is not a sufficient condition to be for getting real eigenvalues. It's not a necessary condition for getting real eigenvalues. It's a sufficient condition. In some books, you may find that they have defined this positive definiteness without taking this assumption that symmetry or Hermitian. Then this is not guaranteed. For that, what generally they do, either they have to write the real part of X transpose Mx would be greater than 0 for all X, either this one, or you have to define the definiteness on the Hermitian version, m plus m star. Okay, that is like mostly you will find that is then they will, that is if it is not assumed, then the same definition they write here m would be replaced by m plus m transpose or m plus m star. That is they can work, or that it will be safe to work on the symmetric part. Because whether m is symmetric or not, m plus m transpose will always be symmetric, right? That is the logic. Either you have to use this one or you have to use this one, okay? To avoid all those hazards, in most of the resources you will find that they start with the symmetry assumption, okay? There are very interesting properties of positive definite matrices. One of them, as you mentioned, that is for a positive definite matrix, all the eigenvalues are positive. But please remember, that is not the definition. That is quite often we do this mistake. If somebody asks you what is the definition of a positive definite matrix, then you must say this one. The other ones, like they are all the properties of positive definite matrix. Okay. Like you will find that one other definition, like all leading principal minors of a positive definite matrix will always be positive. That is also a property, that is not a definition. Once again, all the leading principal minors of a matrix, if they are all positive, then it is a positive definite matrix. Okay. So similarly, that is like there are a lot. So that list is there in the, also that is in, I think in Scopester book in chapter 4. I will show you, don't worry. At this moment then I am just going back to the book. So as of now, after like 3, 4 and then, so may I erase this part? Here you may take a note that is at this moment you might be thinking that is where we are going to use these positive definite properties of a partition matrix. There are two very important lemmas which we will learn in reverse control. There we will need the proof. One of them is KYP lemma. Maybe nonlinear control also sir will talk about this. I don't know. Then if he goes to passivity or positive real, there he will talk about it. KYP means Kalman, Yakubovich, Popov. Okay. The names are like somebody, they were the big mathematicians. I think all of them were Russian. No, Kalman was a British. Sir Rudolf Kalman. Kalman, Yakubovich, Popov. Yakubovich and Popov, both of them were Russian. One is KYP lemma, another one is BR lemma. BR lemma means bounded real lemma. In both of them, that is we use, even that is when, I hope time won't permit, but if time permits, I will also derive the negative imaginary lemma. In all of them, this should complement lemma. This is one of the key techniques which we use. first mathematician and control theory, Professor R.E. Kalman. He was the father figure for introducing all this linear control theory. This controllability, observability, rank test, and then like decomposition of the stateless matrices, then least square estimation problem. For all this came in the late 60s, or I mean starting from 1958, 59, 60s. Everything were mostly due to Professor R.E. Kalman. He was a British mathematician and control theorist. Can anybody tell me what will be the determinant in this case? With the help of this, with the help of 5C, and also by using the Schur complement lemma, can you tell me what will be the determinant of 5A and B? Into what will happen? You have already seen that one. Just apply your mind and tell me. Oh, here even we don't need to make it zero. The determinant formula is not that complicated. Here you will need to apply the Schur complement. Why? That is, suppose A22 is invertible. Okay. Oh, sorry, A11 is invertible because that one is coming. So then, what will be the Schur complement of the matrix with respect to A11? A22 minus A21 into A11 inverse into A12, provided A11 inverse exists. Okay. Another one, determinant A22 into determinant. What will happen? The Schur complement with respect to A22. So it is A11 minus A12 into A22 inverse into A21. Here provided A22 inverse exists. See. the way how I have written, equals to, then after that a brace. That means one of them, okay? But in the book you will find they have put an equal to between like equals to and then equals to this. That means in the book probably they have written this is equal to and then this is equal to. If you have to write that, then the assumption is both A11 and A22 are invertible. But it may not be always the case. That is, you may not expect that is everywhere both the diagonal entries would be invertible. If one of them is invertible, then accordingly you will have to write the formula. Okay?
So maybe sometimes both cannot be applicable together.
Sorry, Paritra?
So maybe sometimes both formula cannot be applicable.
Exactly.
So but here we are using sorry, non-invertible means determinant 0.
Bolo?
So determinant might be non-zero, even if it is not invertible. Determinant is connected to
No. But the problem is if it is not, suppose if A11 and A22, if they are not invertible, you cannot write this expression, right? That is the problem. Finally, what would be the determinant, that we don't know. But for the validity of that expression, here you need, that is, this inverse must exist, this inverse must exist, right? For that, you will have to ensure whether the inverse exists or not, okay? And earlier what I wrote, that is, suppose, if it is upper triangular or lower triangular, then it will be determinant of A11 into determinant of A22. Earlier that I made that mistake only, that is I started with the lower triangular or upper triangular, but in any case since the one of this is 0, so ultimately the determinant of one part will be 0. If you use the first expression, immediately that is it would come. Right? This is the standard expression. So if one of the off diagonal entries is 0, then it will come down to this one, right? You put here, it is either A12 or A21. If they are 0, then immediately it would result, right? What happened, Kanika? Not understanding? Is it fine?
Sir, like determinant of A1 by determinant of something that was according to like A11, right?
Oh, you wish to see that is how it has been done. Okay, that expression is also there. Everyone, please check the expression A.60 or A.50. Anyone? 50. You see that partition matrix A11, 12, 21, 22 can be decomposed as a product of 3 matrices. And now already in the A.9 you have got determinant of A1 into A2 equals to determinant of A1 into determinant of A2. See, A.9. Now come back to A.15. You have 3 matrices. You consider as if the first one is one block and the 2 other another block. So determinant of the product of those 3 component matrices is the product of the determinant of individual matrices, right? So then what will be the determinant of the first one? It is a lower triangular matrix. Diagonals are I. So determinant of that matrix would be 1 only. Okay? Then determinant of the third component. It is upper triangular matrix. The diagonals are the I. So again it would be 1. And then the matrix in between, that is a block diagonal matrix. So it would be determinant of A11 into determinant of X. And what is my X? That is the Schur complement. In this way actually it comes. That is the proof. Thank you, Konika, for asking this one, because I didn't show the proof, but maybe all of you were thinking that is how does it come. So that is the basically formula. So if I write it, that is this partition matrix can be written in the product of three matrices. There is I00 and then A 2 1 1 1 inverse, then I0, sorry, that is A11. Here I am considering that is A11 to be the invertible one, right? So A11 0, this is the Schur complement. So the Schur complement I am writing by X. So where X means I have considered A11 to be the invertible. So what is the Schur complement with respect to A11? You have to start from this element and then this will go in the clockwise direction. So it must start with A22. So this is A22 minus A21 into A11 inverse into A12, right? Now here you have a third component. So what is that third component? This one, it starts from a lower triangular matrix. So the other one would be an upper triangular matrix with the diagonal entries to be identity. And then here if you see the pattern is, of course, that is when I am assuming A11 to be invertible, so I cannot suddenly write A22 inverse. In one of the formula, A11 inverse would be used. In other formula, A22 inverse would be used. Now here if the assumption or supposition, whatever you write, A11 inverse exists. In that case, I am writing the formula. In the book, you can find A16 gives you the formula when A22 inverse is assumed to be existent. Okay. So for this one, you see here another pattern is there. All of you, please look at my board. A21, A11 inverse. When it's a this type of matrix, that means lower triangular. So lower triangular means A11 inverse is coming, and then following that this direction A22 will go from here. So A22 into A11 inverse. Okay. Then when it's a upper triangular matrix, again some A inverse, A11 inverse would be there. Now along the same direction, which element is next to A11? A12, right? So that's why it will be here A12. That is the pattern. If you if you simplify this product of three matrices, it will come back. Now what I said, the determinant of this one is basically 1. Determinant of this one is also 1. Determinant of this matrix is determinant of A11 into determinant of X. That's through that only that formula came out. Okay? এইটা একটু বন্ধ করে পিছনের একটা চালিয়ে দাও না, এই জায়গাটা বেশি ঠান্ডা হয়ে যাচ্ছে। না এটার থেকে আওয়াজ আসছে না, ঠিক আছে একটু বন্ধই গরম করে দাও, কারণ আমাদের সবারই জ্বর ছিল, আওয়াজ লেগে গেলে বিপদ হয়ে যাবে। এক্সামও আসছে। আসলে এগুলো খুব হাই পাওয়ার এসি, ওই জন্য মোটামুটি মিনিট 15 চললেই প্রচুর ঠান্ডা হয়। Since what we were writing, and the determinant of C into M, okay? Let M belong to R, N cross N, and C belong to R, okay? That is C to the power N into determinant of M. That is one of the formula. Determinant of M inverse equal to 1 by determinant of M provided M inverse exists. All these clauses are really very important, okay? Because suppose like you will often find that in papers or even in for when we write it in a either in a casual manner or who are not that experienced in such kind of formulas, the assumptions or the starting points would be missing. That indicates that is you are not a like mature student. Because you see, although like these are small issues, but still if one has to be 100% technically correct, then you cannot write this formula without this, isn't it? Because we are writing determinant M inverse. For that, here it must be assumed or it must be provided that yes, M inverse exists. Only after that we can talk about the determinant of an inverse of a matrix, right? So that's why for writing any types of formula or mathematical statement, all the prerequisites or the suppositions must be listed before you start writing the actual thing, okay?
So why did you write C to the power N?
Because here if you see that is here the order or the dimension is n cross n. So you expand the determinant, you will see that C would be that is C would come into that product form n number of times. here you need some illustration. That is, we cannot write isn't it? That is the eigenvalues of the sum of two matrices is never equal to the sum of the eigenvalues of individual matrices, right? Similarly, isn't it? So, with respect to these two, we have two particular cases. So, that's why they are important. What I meant to say, in general, this is the rule. That means the sum of the eigenvalues or the product of the eigenvalues, they do not follow these identities, right? But these two are special cases. Here, like I plus mn and I plus nm. So, what is the meaning of this property? That is the non-zero eigenvalues of both these pairs will remain the same. Some of the zero eigenvalues will also be same, but if you count the multiplicity, maybe they will not match. Because suppose if this m into n, suppose this dimension is coming n cross n, and small n cross n, and nm, its dimension is coming m cross n, then what will happen? The number of zero eigenvalues will not match. If the dimension of nm and mn, if both of them match, then it's not a problem. Then even for the zero eigenvalues also it will match. But if they are not the same, suppose this is giving you 3 cross 3, like the other day I took an example, and this one suppose giving 2 cross 2, then the multiplicity of the zero eigenvalues, they will not match. So here you have to write there is the non-zero eigenvalues of I plus mn and I plus nm will remain the same. That is the property. And then it is the second part what I wrote, that is eigenvalues of m plus a scaled identity matrix is equal to the eigenvalues of the original matrix plus the scaling factor. Once again, the eigenvalues of a matrix plus a scaled identity matrix. C into I means a scaled identity matrix. That is equals to the scaling factor C plus the original eigenvalues. Okay, that is the property. All of them can be proved. That is, at this moment I am only introducing the properties and just getting you familiarized with that, but all of them can be proved. Okay. The diagonalization I am not writing, I am directly going to the other properties of eigenvalues. Right? The determinant of a matrix is the product of all the eigenvalues, right? And trace of a matrix is the summation of all the eigenvalues. Okay. Now check the other properties of the eigenvalues. Page 514. No, mk directly, sorry, that is lambda I to the power k. I made a mistake. Of course, it would be like c into this one is c into lambda I to the this one, and that would be finally the identity is lambda I to the power k. Okay. This is actually the other part of 9, since it is coming to in the same category, that is either we are adding something with a matrix or we are multiplying a matrix by something, so that's why I made this number as 9c. You see this part, the where I put 9a, this has been written as here on the page 514, property number 9. Read out the statement. Consider an L cross M matrix A and M cross L matrix B. Then the L cross L matrix AB and the M cross N matrix BA have the same non-zero eigenvalues. Okay, here what I wrote in terms of I, even if I is not there, still the relation will hold. Okay. To be more specific, assume L greater than M, then the matrix AB has the same M eigenvalues as BA plus L minus M eigenvalues, which are identically equal to 0. That is I explained in terms of if that is 3 by 3, it will have more 0 eigenvalues, right? So in that case, you can adjust the number. That is the property about it. If you see then property number 11, or no, property number 10, eigenvalues. I think number 10 also that you know, right? That is the eigenvalues remain the same under the similarity transformation. Let M bar, let isn't it? After that, could you please see the property number 11? The same eigenvector matrix diagonalizes the matrix A and the matrix I plus A whole inverse. That means, suppose that is, if you find the diagonalizing matrix for N, the same matrix will diagonalize I plus N as well. Can we try to prove? Please check that proof and let me do that. That part is fine. We have to check whether this P remains the diagonalizing matrix for I plus M as well or not, right? Sorry, I plus M inverse. Please check what is the property, what they have written. That is the same eigenvector diagonalizes the matrix A and the matrix I plus A whole inverse. So here we have to check, that is what it becomes. That is, suppose P inverse, and then in place of M I am going to write I plus M whole inverse into P. Can anybody simplify this? No. At this, how can it be pushed through? In between there is no P. You just here you have like two inverses and this one not inverse. Just try to, what is the formula for, suppose if you have A inverse, B inverse, C inverse, then what is the compact inverse?
C inverse, B inverse. So reverse.
Like what I wanted to mean, that is A, B, C whole inverse. What is that formula? B inverse, A inverse. Now if this is given, what will be this form? That's what I wanted to mean. I want that a whole inverse formula for this bit. Suppose this is as if A inverse, B inverse, C inverse. Then it is P inverse I plus M into P whole inverse. Now you compute the pre and post multiplication. Then the first one would be going to be P inverse into P. That would become I, right? And the second one, same P inverse MP. That would be M diagonal. The second one, P inverse MP. That would be M diagonal. Originally it is under the inverse. That's what.
So basically using the formula to have a result from this equation.
It is simply, that is an, like, what should I say, an auxiliary property of the diagonalization. The first one is my purely diagonalization, right? If your similarity transformation matrix consists of all the linearly independent eigenvectors, then here you can write where A di equals to lambda I di. I separately wrote that one so that you can easily understand that this is a eigenvector. This matrix consists of all the eigenvectors, right? So this is the diagonalizing matrix. So the property says that the diagonalizing matrix, the same diagonalizing matrix can diagonalize the I plus M inverse as well. It is here this diagonal matrix for M. Now the same matrix P can diagonalize I plus M whole inverse. Please note, not only M inverse. Certainly for M inverse, the diagonalizing matrix is not P.
For I plus M inverse is diagonal.
The same. Number 14, if you see there, they mention about Gershgoring-Higgs theorem, but that is not required. Probably Gershgoring-Higgs theorem I mentioned during the E601, if you remember. I only mentioned, I didn't like discuss that. But at least for us it will not be required at this moment. Then property 13, the eigenvalues of a Hermitian matrix are real. You see that which we already discussed. Now I will ask you to show me the proof. All of you please try this one. Okay, not now, later. proof of property 13. That is, suppose if you have a matrix that is real or Hermitian, you have to show that its eigenvalues would be real. Okay. If you have a matrix which is either symmetric or Hermitian, then all its eigenvalues would be real. That too you must try. And if you can do that, immediately the next property will automatically prove. See the property number 14. A Hermitian matrix is positive definite if all of its eigenvalues are positive. So here I wanted you to show that if suppose my n is a positive definite matrix, so you have to show that is a lambda I will all be positive. So that means here what I am writing, that is C, n positive definite, that implies lambda I of n will all be greater than 0. So you have to prove this, okay? And here, why did I say that this is a part of property 13? Because in property 13, you will be proving that if the matrix is symmetric or Hermitian, then the eigenvalues will be all real. So now, while you define a positive definite matrix, already we use that supposition, m equals to m transpose. Along with that, we further have a condition that it is positive definite, okay? So then these two would be too much related. So if you can prove 13, automatically the 14 will also be proved. Okay, that is a small home task for all of you. Now, could you please see point 3, singular value decomposition. Definition A.3, SVD, any complex L cross M matrix. Please check that one. So last day we were discussing about SVD. This is just I'm introducing the properties, but for SVD we have to understand its geometric significance as well. last day we were writing the dimensions of the blocks, right? Now, if you see that is this sigma, that is the matrix which contains all the singular values. Singular values are the gains of a system. Okay, that is at this moment. There is, you may not understand why I am saying they are the gain, but when we will learn the geometric interpretation, then it will be clear. At this moment, we are just understanding this is as if the SVD is a matrix decomposition process. Okay, so whenever that is we find this sigma, that is the matrix of singular values, they are always ordered from maximum to minimum. This sigma 1, that is, this is always the maximum one, the sigma max. Okay, and then the last one that is in the form of, that is how many, then this is the lowest one, but some sigma can be 0 as well, so that will be the sigma minimum. It is not that this all the sigma I, they will always be positive. It is not that. It can be like negative, it can be 0 as well. So what should I write? That is this lambda I, that is greater than equals to 0 for all I. So lambda, this sigma values are always positive. At the minimum it can be 0, but it can never be negative. Okay. Now that is here, the way I have written, that is this sigma 1 up to r. So all the non-zero sigma values I have put together. Okay. In that way, this block here, see, that is, this is the sigma. I am just partitioning into a 2 by 2 grid. So this part, its dimension will be how much? R cross R. And if the overall dimension is m cross n, then can't we resolve the dimensions of the other 3 partitions? So this one, that is what will be? That is how many here? M r number of rows. As a whole, m number of rows. So what is the number of m minus r? So its dimension would be m minus r cross r. The column number must be the same. Once again, the total number of rows is n. This square block takes r number of rows. How many remaining? M minus r. And then this part should have the same column. That's why the number of column is r, right? Then what is the dimension of this 0? Number of rows same r, and number of columns. Here it has already taken r number of columns. Total number of column is m. So here, what is the number of column? M minus r. So this dimension is r cross n minus r. Fine. And then lastly, what is the dimension of this partition? M minus r cross n minus r. Right? Now we have to find out, that is how we can derive, or like given a matrix, how we can find this sigma and this input output singular vectors, right? That much we have to find. Let's see. You first check, that is what they have written, check whether you can understand. See, first of all, sigma they have written in the form of sigma 1 0. This is the this is the reason why they have partitioned it, because some of the sigma values can be 0. So if you see, there is A28, they have written that whole sigma, that is first of all one matrix sigma 1, then the remaining 0. Okay, that 0 means the remaining all the 0 values. Here I have partitioned it into 4, they have partitioned it just into 2. That is the only difference. If you go to the next page, then you see that is sigma can be partitioned either vertically or even horizontally. A28 shows vertical partition, like A29 shows horizontal partition, but this is the most generic. So that's why that is I use this one. This is shown in Kenninghau's book. I found that is like instead of taking a horizontal partition or a vertical partition, if you partition like this, it will be much more realizable and much more intuitive. So that's why I'm using this one. The source is Kenninghau's book. And A20 they have given, that is the sigma 1, that is the diagonal of sigma 1, small sigma 1, small sigma 2 up to small sigma k. Okay. And then the sigma bar or sigma max, whatever you write, that is for the sigma 1, that is the, in that way it is always ordered. So sigma 1, sigma 2. You check the remaining things. And check the remaining things means, can you identify how to find out these singular values? Let's take a break, okay? I hope the class is not boring and it would be helpful for all of you. Even sometimes in nonlinear and especially in optimal also, you will see many matrix computation would be required. Hey, একটুখানি তাহলে বন্ধ করে দাও। While you took the break, I was asking the remaining students that what are the definitions of normal matrix, orthogonal matrix, and unitary matrix. Can anybody tell me? First of all, orthogonal. And then how could you check that? Maybe what is the definition? That is if A is orthogonal. If A inverse equals to M transpose, isn't it? Then Horitro, what you told, that is all the columns, they must be orthogonal immediately. Through this, that property can be easily established, right? M inverse equals to M transpose. Now, for the same thing, let M, if the field is complex, suppose it belongs to C n cross n, then M is called an unitary matrix if M inverse equals to M star. M star means this term is complex conjugate transpose, okay? That is the only difference. And normal matrices. Isn't it? What is the idempotent matrix? work is you check what is projection matrix and projection operator. Okay, that is a small homework. Projection matrix and projection operator. First of all, you have to learn what is a projection. This projection, not only that we have learned it after coming to engineering, we knew it since our maybe class 10 level, where first of all when you learn in the physics that work done means Fs cos theta, like force into the cosine of the displacement. Then there only that is we learn that is if the force is not along the direction of the displacement, you have to take the projection along the same line, right? From there onwards we like started working with projection. Now as a mathematical property you might not have learned that, but as a like property which is used in physics, that experience we had since long time. But now then you should check what is a projection and then projection operator and projection matrix. Then you will find idempotent matrices are also projection matrix. Anyways, that is why we were discussing, that is because we were discussing singular Faraday decomposition, right? But all of a sudden, why did I ask about this orthogonal unitary matrices? Because this U and V, they are not ordinary matrices. They have that property of orthogonal. If it is real or if it is complex, then U and V will be unitary matrices. Okay? That means this U will satisfy the property U equals to U transpose and V equals to V transpose. Sorry, that is U inverse. U inverse equals to U transpose and V inverse equals to V transpose. In that relation, I ask you those questions, okay? So, if it is real, then it will be transpose, and if it is complex, then U inverse would be equals to U star as well as V inverse would be equals to V star. When real, when are complex. U is called the left eigenvector, left singular vector or output singular vector. V is called right singular vector or input singular vector. Okay. That is where this geometric interpretation will come. Geometric interpretation in the sense that suppose you are getting an output vector or y, suppose a into x. Okay. Then that is you decompose A into SVD. What will happen? U sigma V transpose X. Okay. See this sigma. This is like M fat or a tall matrix. I mean M cross N, but it is a kind of a diagonal, right? That is, if you see this structure, this part is entirely diagonal, and the remaining ones of all zero, right? Now that is, if you see, that is how is the output vector that is getting produced. Is V transpose, that is a matrix which is operating on the vector X. So suppose that X is something like this is X. This is suppose X. Then what happens when this, and this is a unitary matrix. And the one property of the unitary matrix is that it will always produce rotation, but no change in the scaling. Okay. So, like first of all, when this V transpose is operating on X, then it will give an input rotation. It can be clockwise, it can be anti-clockwise. So, suppose you are getting this one, that is from this you are getting here. This is due to V transpose. Okay. So, you have got something. Suppose this is X dash. After that, the sigma is going to operate on V transpose X. The sigma is a mostly diagonal matrix of the diagonal elements, and the remaining ones is 0. That won't produce any rotation. That will only change the eigenvalues of this whole matrix. Okay. So it will be only, that is finally, this is n cross 1. This is n cross n. Sorry. So as a whole, V transpose X, that will be a vector in cross 1. So this matrix is going to work on that vector. So that part will either either it will stretch the vector, that means either the magnitude will increase or decrease. So here what will happen, that is, suppose it along the same way, it can either extend or it can even, that is, shrink. So either it will expand or it will shrink. Suppose that part is my X bar. After that, what will happen? This U is going to work on that. Okay, so what is about this? This is my M cross N. So M cross N into N cross N into N cross 1. As a whole, what would be the dimension? N cross 1. This is the version X dot, that is M cross 1. When I wrote that is X dash, that was my M cross 1. Now you see that U, another unitary matrix which will provide a rotation, not any scaling of the eigenvalues or of the vector. So that's why now this is come, this will appear as a final rotation. So suppose from this one it will go suppose this is my X double bar, or suppose this is X hat. Another rotation. So this is suppose for theta 1, that rotation is due to V transpose. Then a scaling of the magnitude which is due to this sigma. After that, another rotation, suppose this angle I am denoting by theta 2. Theta 2. And finally, it is suppose my X hat. X hat is nothing but Y. Okay. So,
So theta 2 will be from the
so from X we get X prime, right? That is because of T transpose. From X prime to we get X bar, that is because of sigma. And then from X bar we get X hat, which is nothing but Y, that is because of U. So here this is one rotation, or we call the input rotation, then scaling in magnitude, then another rotation. This is actually, in short, that is the geometric interpretation of SVD. But why this is one of the very important tool in control theory, especially in multivariable control theory, I will show you. Now this is about this rotation and then scaling. So that's why it helps us to understand when you have a multivariable system, multiple channel, then in which channel the gain is maximum, in which channel the gain is minimum. In like finding those kind of information, SVD really helps us. Ms. Augustin took there is an example, and I think in chapter 3 or 4, I will take up that on board and I will explain. Okay. Have you understood this? What I have done here? Now, so what we have learned is U and V, they are unitary matrices, okay? And we have like partially understood the geometric operations or geometric interpretation caused by the operations within the SVD, right? And although that is just, that's why I said that partially, because until I just take up that example, you won't be able to understand this, why this is so much important for multivariable control theory. Anyway, today I am not studying that one because it is a completely different discussion. At this moment I am coming back to the SVD. Here now we are left with 3 exercises, 3 things. That is how we can find out the output singular vectors, that means U1, U2, Un. Then how can we find this V1, V2, Vn, and most importantly this sigma 1, sigma 2 up to sigma r. Can anybody tell me how we can find it? That is, if you see the book, you will just check in the relation A32. They wrote that the singular values is the square root of like lambda I A star A. That is what they have written. That is this sigma I, that is the root over lambda I of A star or oh, I wrote M, so I must write it. M star M is same as square root of lambda I M star. That is the relation they wrote. Now that is like, can we prove this? Any idea? Anybody? So then if we rely on that formula, that is they are giving this one. So if they are right, then from that we can get a hint that is maybe if we can find out the expression for finding the eigenvalues of this one of these matrices, either M star M or M star, then let's see what happens. Because at this moment we are not sure about the sigma, but if you temporarily rely on that, then we may try to find out the eigenvalues of this matrix. Let's see, that is like why they have written this one. So that is when you have the fundamental equation, that is lambda V equals to AV, and then from that we get eigenvalue eigenvector equation, that is lambda I minus A into V equals to 0. So that is the equation, like quite standard, we always use that for finding out the eigenvalue eigenvectors. Now that is instead of A, if you find that M transpose M or M transpose, then what will happen? That is, if I ask you to do, that is determinant of lambda I minus M transpose M.
Lambda will give the singular values of M.
That we will check later, because from this that property is not readily coming, right? That is, at this point what we are trying to understand, that is what is the, are you understanding what I am trying to say? At this moment we are not sure about the sigma. That means we have learned that sigma is a separate quantity which is called the singular values. Now we don't know, that is, whether there is a relation between sigma and the eigenvalues of M. What I wanted to mean, that is sigma I of M versus lambda I of M. That is one question. Secondly, sigma I of M versus lambda I of M star M. That is my second question. And the third one is sigma I of M versus lambda I of MM transpose. That is my third question. Are you now getting what I am trying to say? We have learned sigma as a separate entity, singular values. Now we are trying to establish a relation that with the eigenvalues of M as well, but we are not sure about that. But why, you can ask the result, why you are unnecessarily complicating the things? Why do you at all need to find out whether there exists any relationship between the singular values of a matrix and its eigenvalues? But actually here at this moment we don't know how to compute the sigma I. So we have to find out a relation, or we have to find out a technique by which we can at least numerically calculate the values of sigma, right? That's what, through that we are proceeding, like we are trying to reach in that direction. That is how we can find out the values of sigma. And in that path, we have seen there might be some connection between these newly defined singular values and the eigenvalues of the original matrix or this, right? So we are trying to explore that path. Is it now clear to all of you? That is why we are trying to find that out. Okay. So you see, that is when this is the relation for finding out the eigenvectors. And if somebody asks you that is you find out the eigenvalues, then what would you do? Like simply you will write determinant of lambda I minus a equals to 0. That will be giving you the eigenvalues. Isn't it? That is for eigenvector, this is for eigenvalues, right? Now in the same way, that is if you do it, suppose it is like that, then what will happen? Have you understood the platform? That is why we are trying to compute that. Let's see, that is what does it happen? Determinant of lambda I minus, then is m star m. You use that expansion, SVD expansion. Then m star means so v my m means u sigma v transpose or even v star. So if you take the m star, then what will happen? That is v sigma star u star, and then u sigma v star equals to determinant of lambda I minus v sigma star into sigma. Why? Because u star into y identity, right? Is it fine? Then after this, well, that is if you have problem with this, I can write it just in a slightly different way. And you suppose lambda into v square. I hope it would be even more straightforward, right? Just a few minutes back, we learned that formula. The determinant of a product of a few matrices is the product of the individual determinants, right? Then after that, I'm going to write on the top, so that's why I'm using this. it clear? No. Anybody any doubt in this derivation? Now, if I wish to do the same thing with mm star, then what will happen? Isn't it? Exactly the same derivation now which I did with respect to V star, it will now be in terms of U star and U. What I wanted to mean, that is because M star equals to U sigma V star into V sigma star U star, isn't it? So then we will have U sigma star U star. This I you are going to split as U into U star, then you would be taking U and U star common from the left hand side and right hand side. After that, the same operation. Is it now fine? Finally? Now, what is the conclusion? So, finally what we are going to find, that is determinant of lambda I minus, if you see the first one, sigma star into sigma, that is equals to 0. From that, what will be the, what are these eigenvalues? Exactly. So from the, if we do this, or even that is if we put this one like, to be equals to 0, from that what are the sigma values, what are the eigenvalues we will get? Either those are the eigenvalues of sigma star into sigma or sigma into sigma star. Okay. Now finally what is the conclusion? Sigma may not be wholly diagonal, but like if you calculate the product, then finally you see that is what would be, that is now the original relation, that is sigma is root over of the eigenvalues of m star m. Is it now coming? All of you please check that fact. That is initially what I mentioned, that is they wrote that is sigma values, that is singular values, Those are nothing but the square root of the eigenvalues of M transpose M or MM transpose. Now could you see that is why they wrote that relation?
So it will be same as writing root over of eigenvalues of sigma star sigma.
Then the final doubt can be that is why you have to take the square root, right? So if you see that is here ultimately it is coming sigma star sigma. Now that is if you multiply, suppose you have this 4 block. One is for the sigma, this 0, 0, 0 and this transpose into this. Ultimately, won't you get one of the partition which would be the square of the sigma values? That is the relation. That is what I wanted to mean. That is, if you have this kind of, like if you can take any of the examples. Like suppose you have a square block, then here you have a tall zero matrix, here you have a fat zero matrix, and here you have a square zero matrix. Then what will be your sigma transpose? Here because it's a real matrix, so star and T means same. If you do this, then what will happen? That is here they are all the diagonal, right? So even though that is the row column that will interchange, but all the sigmas will be on the same location, and then it would be sigma 1 square, sigma 2 square up to sigma r square, right? So that is here if you correct, that is what will be the eigenvalue, that is these eigenvalues would be nothing but the eigenvalues of sigma star into sigma, but they are nothing but the square of the singular values. That's why that is this. Is it now clear for all of you? So once again, when that is you are taking this M star M or MM star, after all these cancellations or then after that is like simplifying this formula, you are getting either sigma into sigma star or you are getting sigma star into sigma. If you compute that, then you will find that is ultimately it is coming sigma 1 square, sigma 2 square up to sigma r square and some like zeros here and there. But as a whole it would be a square matrix, right? Why it would be a square matrix? M cross M always be careful about the dimension. What is the dimension? N cross M. This is M cross N. So together it would be N cross N. So it's a square matrix. Okay. If it is sigma into sigma star, then also M cross N. This is M cross M. So together this is M cross M. So ultimately that is what will be this pattern. Sigma 1, sigma 2 up to sigma r. Now suppose this is M cross M. I am just showing with respect to this. This whole dimension, this is r cross r. Right? So here you have 0, here you have 0, here you have 0. Okay? So then what is this dimension? M minus r cross r. Right? This dimension? This will be your r cross M minus r. And this will be your M minus r cross M minus r. So this is going to be a always, whether this is sigma into sigma star or sigma star into sigma, always it would be a square matrix with most of the elements being the square of the singular values. Okay? So that is the reason, that is finally when you are getting the eigenvalues, they are nothing but the eigenvalues of the that is original, sorry, that is when you are doing this determinant of lambda I minus m star m equals to 0. Finally, this gets simplified to this one, determinant of lambda I minus sigma star sigma. So sigma star into sigma, that will give you the square of the singular values, right? And ultimately, when you are finding the lambda, they are nothing but the lambda of m star m. So from this expression, like what you have finally, what we are finding out, they are nothing but the eigenvalues of m star m, right? And what we have seen, that is what are these? They are it is a square matrix whose it is a diagonal square matrix whose most of the elements are the square of the singular values, right? So that's why, like once again, you start from this expression, that is determinant of lambda I minus m star m equals to 0. Because this is not the starting expression, this is the final expression which we have got. This is the starting expression. So the lambda which we are now finding, that is actually the lambda of m star m, or even the mm star. So these lambda values are nothing but the square of the singular values. This second statement, square of the singular values, that is coming from this expression, and that too because of this structure. So eigenvalues of mm star or rather m star m is nothing but the square of the singular values. Is it not clear for all of you? If I now write what are these eigenvectors? This is eigenvectors with respect to m star m, right? Because earlier when I wrote, that is the usual is when you write that is lambda I minus a into vi, if you equate it to 0 and then if you find out the solution of vi, that gives you the eigenvector corresponding to lambda I. So similar to that, if you now use this equation, then the eigenvectors which you are going to have, they are the eigenvectors with respect to the eigenvalues of m star m. And now the same, the eigenvalues of m star m means the square of the singular values of the m. Yes. What are these in the xi? So which is what I just said. That is, and then before that, can you tell me that what will be the dimension? M star m? N cross n, right? This belongs to R n cross 1. They are nothing but the right singular vectors. All the vi candidates. And similarly, if you solve this one, lambda I minus mm star. Suppose here you are writing, suppose yi equals to 0. then what is the dimension of this yi? Mm star means this one, m cross n. So,
What is the left eigenvector? Y.
no, this is like standard eigenvector. You are considering m star m to be one matrix, and then the standard eigenvector, like this. Compare this with this, as if A has been replaced by m star m.
So second one.
Second one, but here also, here you are considering this whole block to be one matrix, because when we found the eigenvalues, there we didn't consider any other thing, right? That's why. It is for both the cases we are finding out the standard eigenvectors or the right eigenvectors only. Okay. So here if you see yi, what is the dimension? That will be, that is R n cross 1. So now they will all be the ui's, and it will all be the vi's. So, you wanted to ask that if I would have considered the left eigenvectors which are the same, right? Yes, they will be the same only. It is in this case, that is if I consider the left eigenvector of this combination only, that would have been this one. Right. So once again, that is what the takeaway points. These eigenvalues of m star m or mm star, they are nothing but the square of the singular vectors. Sorry, square of the singular values. And then the eigenvectors associated with this lambda, they will be either the right singular vectors or left singular vectors, depending upon whether you are writing mm star or m star m. Okay. Today we have learned many things, right? Although they are prerequisite, but anyway, these are all part of the multivariable control. As I told you, there is a robust control. If you have to learn that, then first we need to understand or learn the basics of multivariable control. So that's why I am doing all this, because if I would have directly started robust control, then during the derivations, when all these things would have started appearing, then you may find it troublesome. Okay. Anyone, any doubt? Fine, all the things? Acha, if I ask you that what is the rank of a matrix, please explain in a simple word. What would you say?
Independent column matrix of a matrix is rank of a matrix.
Independent?
Column vectors.
But why did you say column vectors? It can be other way around.
The lower number.
The minimum of the independent number of rows and columns, right? There are few other ways by which also you can define the rank.
Dimension of column space.
It can be row space as well, right? It is lesser.
Minimum
Because
of
what you
column.
said usually then is we take the term column in the sense that will be minimum, but the situation changes if you take a tall matrix. Like if it is a tall matrix or a fat matrix, then the situation would have been different, right? If it is a square matrix, then the dimensionality or there is a minimum of them, whether it is rows and column, that will be the same, but that is not true for the square matrices, right? So okay, one definition is the minimum of independent columns or rows, right? That is one. Then the second one, what is the thing you just said? Dimension. That is also the minimum of the dimension of the row space and the column space. Then
image space.
it is the same as column space, right? What are the other things? With respect to SVD, can anybody define
So value of R.
number of non-zero singular values?
Value of R.
Exactly. There is number of the non-zero singular values. So here that is when I know with respect to R, so then R would be the rank. Any other? From the rank nullity theorem also we can find, right? If you can find out the zero eigenvalues, from that also we can find the rank. Although that may not be a definition, but if somebody asks you what is the rank of a matrix, from the rank nullity theorem also you can find, isn't it? And one more, number of non-zero principal minors. I hope that we read a long back. Number of non-zero principal minors. Non-zero principal minors means जिनका determinant zero नहीं है. So in different way we can decide the rank. Okay. And even that is one of the students once defined, that is, suppose if you transform a matrix into RRE form, row reduced echelon form, then the number of non-zero pivot elements, from that also we can define the rank. So there are at least 6 to 7 different ways by which we can define the rank, but I believe the most straightforward is the number of independent rows and columns, whichever is minimum. Okay, so next day, that is, we would finish the norms, and immediately that is, we will, as soon as possible, we will have to start the uncertainty part. Okay. I hope today's class has been useful for all of you. তোমরা এই